Hello, in this video I'm going to solve the following problem for you. So let us read the problem. A substance has an isothermal compressibility kappa equals to A times T cubed over B squared and an expansivity beta equals to B times T squared over P. Of course here P is the pressure and T is the absolute temperature, where A and B are constants. Find the equation of a state of the substance and the ratio of A over B. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do your calculations correctly, these are the answers that you will get. The equation of a state will read like this: V equals to V naught times exponential of A times T cubed over P, and the ratio of A over B is equal to 1/3. Okay, so now let us solve this problem. So you know that in thermodynamics, the most important question that we can ask about a system is that what the equation of a state of that system is. Okay, and this is the reason that we are interested in kappa and beta in the first place, because fairly simply we can measure them in the laboratory and then find the relation between K and beta. Because you know that in thermodynamics we have three variables, say P, the pressure, and V, the molar volume, and then T, the temperature. And then an equation of this form is called the equation of a state. So it means that we need to find the relation between three variables. Here V, the molar volume, is defined to be the volume divided by the number of moles. Okay? So in order to find equation of a state, then I have three variables to connect. Okay, so might be that it's hard because then I have to set up an experiment in a way that can keep track of all those variables simultaneously, which is hard. This is why the notion of kappa and beta could be useful. So how beta is defined? Beta is defined as 1 over capital V, partial derivative of capital V with respect to the temperature when the pressure is kept constant. Okay, so then you see that here I need only to take care of two variables at a time because I am keeping the pressure constant. So I can set up experiments and then keep the pressure constant and check how the volume changes with respect to the change in temperature. Okay, so this is easier to understand and to explore rather than understanding the relation between these three coordinates, these three variables. Okay, and of course here this is the volume, but I can rewrite this in terms of the molar volume, because here the volume becomes N times V, and if I put N times V here and N times V there, these N's are cancelled, so this can be written as 1 over B partial derivative of V with respect to the temperature when the pressure is kept constant. And the definition of kappa is minus 1 over V partial derivative of V, this time with respect to the pressure when temperature is constant. Again, calculating kappa, understanding kappa is easier than understanding the equation of a state. But the good news is that if I know them, okay, then I can find the equation of a state, and that is the purpose of this exercise in this book. Okay, again, I can write it as in terms of the molar volume as this. Okay. Now, let us say that V is a function, because I know that V should be a function of the other two variables. So let us write dV for that. Then it means that it becomes partial derivative of V with respect to the temperature when the pressure is constant multiplied by dt plus partial derivative of V with respect to the pressure when T is kept constant times dP. So here I'm assuming that V is a function of is a function of t and p, and I am writing its differential. And of course, you see here, that is exactly what is appearing here. So that is nothing except beta times v. So this expression is beta times v times dt. And that expression is here. It becomes minus kappa v. So it becomes minus kappa v dp. And now if I divide everything by v, the left-hand side will be dv over v. The right-hand side will be beta dt minus kappa dp. And this is a generic formula in thermodynamics. So far, I haven't used the information given in the problem. This is a completely generic, formula. But now I can take advantage of those information. So I would write dv over v is equal to, instead of beta, I put that expression in. So b t squared over p dt minus, instead of kappa, I put a times t cubed over p squared dp. Okay. And now how should I go forward? This expression is an exact differential. What do I mean by that? Because you can write it as differential of a function, let's say ln of v here. Okay? The derivative of ln of v is 1 over v, and if you take the differential of that, it becomes dv over v. So this means that the left-hand side is an exact differential, and this is supposed to be equal to an exact differential, so it means that the right-hand side should also be an exact differential. For this one to be an exact differential, a necessary condition is that the derivative of this expression, derivative of bt squared over p, this is a theorem in multivariable calculus. So if this is supposed to be an exact differential, the derivative of this expression with respect to the other variable p should match with the derivative of this one, a t cubed p squared, with respect to the other variable t. This is a necessary condition for this expression to be an exact differential. Okay, so let us just do this. When I take the derivative of this and p is variable, it means that everything else is supposed to be constant. Okay, so the derivative of 1 over x is minus 1 over x squared. So here I am giving the role of x to the pressure. So this becomes minus 1 over p squared, but I also have this on top. It becomes this. And now here I want to differentiate this expression when t is variable and everything else is supposed to be constant. So you can compare it with x to the power of 3. The derivative of x to the power 3 is 3x squared. So the derivative here becomes minus 3at squared over p squared. And these two should be equal. Okay? And now you see that p squared and p squared, t squared, the minus sign and the minus sign are gone. What is left here is b. What is left there is 3a. Yes, so this means that a over b is 1 over 3, as is wanted in the problem. Okay, but this does not on its own guarantee that this is an exact differential. We need to see that if it is exact differential or not. So, but I know that b is supposed to be 3a. So the right-hand side here, with the new piece of information that I have available, instead of b I put 3a, and t squared over p dt minus at cubed p squared dp. Okay, is it an exact differential now? This is an exact differential. If you can guess, that is working. If not, you need to find it if it is possible. So I would say that this expression, if this is going to be an exact differential, there should be a function of two variables t and p, so that the partial derivative of that function with respect to the variable t should be equal to that expression, 3a t squared over p. So you see, if this is going to be an exact differential, there should be a function f of the variables t and p, so that when I differentiate that function with respect to t, it gives me this. And when I differentiate the same function, with respect to p this time, it gives me this expression. Yes? So I want to see that is there a function of that type. Okay, so I can start with one of them. I want a function of two variables so that when I differentiate it with respect to t, it becomes this expression. So if I ask you what that function is, you find a primitive function for this when t is your variable. Okay, so what happens from that one? F of t and p becomes equal to a primitive function for this when t is your variable. So it means 3a and p can be considered constants, and if I ask you what a primitive function of t squared is when t is variable, it becomes t to the power of 3 over 3. So this becomes 3a over p, and a primitive function for t squared becomes 1/3 of t cubed, okay, but plus a constant. Okay, but here the case constant is not necessarily a constant because I am just differentiating with respect to t. So the constant can be any function of p. Okay, of course, being a constant is one scenario, but that's not the whole story. So I would say that might be this is a function of p. Okay, so if I ask you what that function is, so that when I differentiate it with respect to t, it gives me this, you will tell me this plus a function of p, because if I have a function of p and I differentiate it with respect to t, then this will be 0. Okay? And if I simplify this a little bit, this 3 and that 3 are gone, so this becomes this. Yes? So that is f of t and p. But of course, I cannot claim that I found my f because still g is not known. Okay, so I use the second piece of information. I have to take the same function, differentiate it with respect to p, and equate it to this expression and try to find g, this unknown function g. Okay, so what I do, I differentiate with respect to p this time, and then when I differentiate with respect to p, a and t cubed are constant, I have to differentiate 1 over p, but the derivative of 1 over p when p is variable is minus 1 over p squared. So I have a t cubed there. And then I differentiate this when p is variable. So if you don't mind, let me just use the symbol prime for it, because I am not confused here. I have g is a function of one single variable, and when I put prime, I mean the derivative with respect to its own variable p. Okay, this is on the one hand based on my calculation. On the other hand, this expression should be supposed to be equal to that expression. So if I write that one here, okay, so this means that the right-hand side of this should be equal to the right-hand side of this because the left-hand sides are identical. And if I compare them, I would say that g prime of p is 0. Okay, g is a function of one single variable, the pressure, and its derivative with respect to pressure is 0. So this means that this function is indeed a constant. Okay, and if that is the case, I put it back here and I found my f. So f of t and p is equal to a t cubed over p plus a constant. So is the right-hand side, now that I wrote it in that way, is the right-hand side an exact differential? The answer is yes. The differential of which function? Of this function. Okay, so the left hand side is differential of ln of v. The right hand side can also be viewed as the differential of this quantity, yes? Okay, so this means that ln of v is equal to a t3 over p plus a constant. That constant might be different from this constant. So you can write c plus another constant. Let us absorb both of them and call it, I don't know, k. Okay, that's a constant. But I want to find v. So v becomes e to the power of a t cubed p plus k. Of course, I can write it as e to power k, and then I can write it as exponential of a t cubed over p. And e to the power of k, I can call it v naught. So then it means that v is equal to v naught exponential of a t cubed over p. And that is the equation of state. That's an equation between v, t, and p. Okay, so that's an equation of state. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.